Okay, well, hello and welcome back. This is our first video for a while, and we're going to be looking at the measurement and data processing topics, the very last bit of that, which is looking at spectroscopic analysis. Essentially, we're going to look at ways in which we can identify what molecules we've made, particularly looking at organic molecules. The first part of this that we're going to look at is our index of hydrogen deficiency. So for this, the IB wants us to be able to define the degree of unsaturation in a molecule, basically understanding that the degree of unsaturation or index of hydrogen deficiency, as it's called, is used to determine from a molecular formula number of rings or multiple bonds in a molecule. So we can determine if we have something like cyclohexane versus something like cyclohexene, or even if we have hexene versus cyclohexene. 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, and 6. So these molecules would all have a different index of hydrogen deficiency. And then we need to be able to actually calculate the index of hydrogen deficiency given a molecular formula of a compound. Okay, so let's have a look at this. When we talk about the index of hydrogen deficiency, we'll usually see it abbreviated as IHD, and it's essentially a measure of unsaturation of a molecule. Remembering that a saturated molecule has single bonds only, what we're saying is how many hydrogens have been removed from the molecule in the process of making it unsaturated. What this does, of course, is because we lose 2 hydrogens for every double bond that we form, or 4 for every triple bond that we form, we can work out essentially the number of double bonds or triple bonds or ring closures, because we lose 2 hydrogens for every ring closure as well. If you think that going back to hexane, C6H14, and cyclohexane, where we have C6H12. Okay, we've lost 2 hydrogens here in order to make that ring close, for the tail to come around and close in on itself. So essentially what we're saying is that the IHD is a measurement of how many molecules of H2, how much hydrogen gas would I need to put in to hydrogenate away these double bonds to saturate the molecule. So if we had 3 double bonds, it would take 3 hydrogen molecules to break them all. Okay, and in this case, with ethylene, it takes 1 hydrogen molecule to convert it through into ethane. So this is just a numerical value that is telling us how many hydrogen molecules, so how many lots of H2 it would take to saturate the molecule completely. Sorry. So if we think about a simple hydrocarbon, which is just CXHY, every double bond is 1 hydrogen deficiency, every triple bond is 2, and every ring is also 1. So we can get this simple formula here, where 2 times the number of carbons plus 2 minus the number of hydrogens divided by 2 gives me what we call the index of hydrogen deficiency. This is for a molecule that contains only carbon and hydrogen. Okay, so if we think about benzene, the double bonds are each going to count as 1. So we have 1, 2, 3 double bonds. So that would give me an index of hydrogen deficiency of 3. And then 1 more for the ring. So that would be an index of hydrogen deficiency of 4. And our formula for benzene is going to be C6H6. So if we have 6 times 2 plus 2 minus 6, so we're going to get 12, this is 14, okay, minus 6 is 8, and then we're going to divide all of that by 2, we would get to 4 as well. So that's how the formula works if we don't necessarily know the structure of the compound that we're looking at. Okay, when we have other elements present, we need to take those into consideration. Essentially, we could go through and work all of these out. I'll put a link in our document where you can go have a look at this if you want. But for a complex molecule that contains carbon, hydrogen, nitrogen, oxygen, and halogens, we have a different formula. Essentially, oxygen doesn't change the index of hydrogen deficiency in our molecule. So in this case, we ignore the oxygen. You can see it has a 0 subscript here. But we can take basically a half, same as what we had before, 2 times the number of carbons plus 2 minus the number of hydrogens minus the number of halogens, because they just act like hydrogens in our molecule, and then plus the number of nitrogens. Okay, so this just makes it a little bit more complex and allows us to deal with a wider range of molecules. So this can basically simplify down into 2C plus 2 plus N minus H minus X, and then all divided by 2. Let's have a look at some examples. So basically, the questions will ask you to determine the index of hydrogen deficiency from a molecular formula. Okay, so you just need to memorize this formula. It's not given in your data booklet. You do need to know this one, and then substitute it into any molecule that we're given. So if we have C4H8O2, we're going to have 2 times 4 plus 2 minus 8, and then I ignore the oxygens. So I'm going to have 10 minus 8 is 2, and then I'm going to divide all of that by 2 or multiply by half, and we will end up with an IHD of 1, which is exactly what we see down here. Okay, so essentially what this does is we can look at different isomers and things like that. Different structures may have different IHDs. And then we can sort of also work out how they may be going together with some additional information as well. So if we look at methylpropanoate, ethyl ethanoate, and tetrahydro3-furanol, okay, which is one that we don't have to know how to name, but this ring structure with the oxygen in it here is a furan, okay, we can see they all have an index of hydrogen deficiency of 1, and we can go through and calculate those as well, okay. But remembering that if they are, if they're not functional group isomers, if they're put together, sorry, not functional group isomers, but if they are isomers of a compound, they are probably going to have the same IHD because we have to maintain the same molecular formula. So if they have a different IHD, then the bonding is different. So we've put them together in a different way. So they're going to have different functional groups and probably a different molecular formula. Okay, what I want you to do is to pause this video and have a go at calculating each one of these for yourselves. You've got cocaine, cholesterol, aniline, and clonazepam here, which are different drug molecules and biological molecules. Have a go at calculating the IHD for each of these and then come back and check your answers. Okay, hopefully you've had a bit of a go. Let's look at this first one with cocaine. So remembering that our formula would have 2 times the number of carbon would be 34, plus 2 takes me to 36. And then I'm going to minus 21, which is going to take me to 15. Add 1 for nitrogen is 16. Divide by 2 and ignore my oxygen, and I should end up with 8. Hopefully you came up with that as well. If you didn't, go back and review the formula and have a go at the next one. Okay, let's look at cholesterol. Following the same process, you should have come up with an IHD of 5. Aniline should have given you an IHD of 4, and clonazepam should have given you an IHD of 12. Quite a complex molecule there. Hopefully you picked up that we had the Cl as well, which you need to minus along with your hydrogens before adding in 3 for your nitrogen. That's it for IHD. Essentially, it's another formula that you need to add into your repertoire and your toolbox. It's going to come up in the organic section, okay, when we look at structures and the measurement and data section. So remembering that when we want to define this, the IHD provides us a measurement of how many hydrogen molecules would be required to give a saturated molecule, to saturate it out. And it gives how many double bonds, triple bonds, or rings are in the molecule, an idea of the complexity of the bonding to some extent. And this formula is the formula that we need to get onto a flashcard and add to our formula sheets to be able to practice that and make sure that we have that one locked away. There's some practice questions in your textbook. Give them a shot, and I'll see you in class.